Okay, so very good afternoon, everyone. My name is Sumit Kumar. This is the week 5 of this lecture series in which we are studying the soil mechanics geotechnical engineering 1. This course is taught by Professor Dilip Kumar Vaid from Department of Civil Engineering, IIT Kharagpur. I am the PhD scholar at IIT Dhanbad. I am taking this class for solving the problems and other aspects, so that will be helpful for you during your examination when the course gets completed. So before starting, there are some instructions I want to give to you that this course will run for 2 hours continuously for 12 weeks, and in addition to that, due to some network problem, if this call get disconnected, please be remain in the meeting and I will rejoin from there and complete the 2-hour class. In addition to that, the PowerPoint presentation or PDF or content questions, whatever I am discussing over here, will also be shared with you through Google Drive link, and that link is already with you as per my knowledge. And this video is also recorded by me, which will be uploaded on the YouTube, and the link will be shared with you by the NPTEL team. Okay, so that is the basic instructions. And one additional thing I want to add on over here, those who are watching on YouTube later, please try to solve the problems which you are discussing over here by yourself. In addition to that, one common instruction that once the coursework is completed, the question related to that concepts from some standard book you can solve. There are the many soil mechanics book, maybe the Gopal Ranjan Rao or and the basic books are is like these only. Whatever book available with you, maybe in your library, if you are a graduate MBTEC student, so you can got these books and try to solve the problem from that. Then you have get the clarity of the problems. And I thought that might be some of you, most of you are maybe the BTech students or maybe the working professionals. So from next class onward, I might take some of the problems which may be asked in the several competitive exams like the GATE or engineering services. So that will might be more helpful for you. As of now, I have taking the questions which has been taken, which has been given in the course during the previous week only. But additionally, I also had some multiple choice question, but that's not very tough. So I plan to add some problems maybe from the earlier topics and the new topic which is coming ahead related to the engineering services examination, maybe MCQ or maybe some long answer question related to soil mechanics. In addition to that, most of you, if you are the BTech students, you might going to give the GATE examination. So I also try to cover the things which is associated with the soil mechanics, the question related to same, so that if the tricky question come in your direction, you will be able to solve very easy. I have planned like this, and let's see what is possible, not in the today class, from the next class, as what I have planned. Okay, so let's start with the today class. In today class, we are basically reading the Bosniak equation, Westergaard equations, and the question related to same. So this is more or less the numerical concepts which we are associated with on the topic of vertical stress we are going to discuss over here. Okay, so first of all, starting with the vertical stress distribution. So you know that stress develop in soil over here. The basic mechanism we are going to read like this. Basically, we have a soil plane. We have a soil at any place, and the force is applied over here. If we consider the 2D only, the load P or Q, whatever you say, is applied over here, and we want what is the stress developed at this point, which is at distance x and at distance z from this point. like this, and this distance, sorry, and this distance, let me take a eraser, and this distance may be called as r, or whatever you say r, that will be in by the simple Pythagoras theorem. Pythagoras theorem, r square plus z square root under, right? So that basic concepts we pick and we solve the problem mainly with the Bosniak equation and the Westergaard equation. Uh, and the problem associated with the same maybe sometimes come tricky when we move ahead. And in this class, the small problem I have taken, but as I go across this course only, I come to this understanding that I can discuss some tricky problem associated with the same, so that that will be helpful in your examination at the end of this coursework as well. And if you are planning to give some competitive examination there also, it will be helpful. So these things we are going to read. So starting with the basic thing, like whatever written over here, like within the context of the geotechnical engineering analysis, it is convenient to view the in situ soil stresses at a given point in term of component of total stress. As you remember in the previous class, in the topic of the total stress, pore water pressure, effective stress, we have first of all calculated total stress approach. And it is quite evident if you have read across some literature, you come to know that when the in the starting before Carl Tarjagi, the all the analysis is followed out of the total stress approach one. But a lot of structure get built on the total stress approach. But once it has been seen that the many of the structure get damaged, so the term of effective stress comes into picture, in which we have considered that if the pore water pressure is there, it will result in the decrease in the effective stress value. Hence, in association with that, the effective stress approach get the better picture of the stress distribution through the soil. So, in general, in terms of the total stress only, we calculate the stresses in soil in the earlier times. So, over here, the 3 point is mentioned that the stress induced by the weight of the soil above that level, fluid pressure, stress introduced by the externally applied load. So, as you see over here, as you see over there, I have said that the load P is applied over here. So some of the stress due to the soil below these sections, and some other stress get developed due to this load. But over here we are interested in calculating the amount of stress developed at this point due to application of this much load only. And this is not like that the question will be asked in that manner only. Some question may could also be built like this also. Like it has been given that this is a rectangular section in which the load is up, in which load is applied at this and this point, and I want to calculate the stress developed at this cross sections due to all these loaded. So the question could be framed in that direction also. In addition to that, question could also ask that if the load is applied at this point, this point, and I want to calculate the stress developed at the center of this cross section. So the question and solution could be asked and framed in differently in the different situations, right? So the these are the three things, like the stress induced by the weight of the soil above that level, fluid pressure, stress introduced by the externally applied load become very much important. Okay, now moving ahead, now we move to the equations which we used during the calculations. But before that, as I have already mentioned that the Bosnick equation, Westcott equation are the some of the equations which is uh, given by the researchers like the Bosnick and Westcott. So what are the those equations? What are the assumptions and is made during the derivation of those equations, and how they are useful in calculating the vertical stresses at any point below the ground surface in two-dimensional and three-dimensional spaces. Okay, so over here the Bosnick theory say that he has given a solution for finding out the stress component at depth z below the surface of a semi-infinite solid due to a point load acting at the surface of the semi-infinite solid. Okay, so as I already mentioned in the previous slide that what we are going to achieve, that we want to calculate the development of the stress or the load at any cross sections below the ground surface. So he has given the equation for the same only, but for that some assumptions has been made. What are those assumptions? In general, in soil mechanics we assume that soil is isotropic and homogeneous. Over here the important assumptions is made like the soil is elastic, isotropic, homogeneous and semi-infinite medium. The soil is also assumed to be wetless, because if it doesn't assume soil as wetless, then the once we come to the equation, I will elaborate this in detail. As you have seen over here, the three things we have mentioned, that the stress induced by the weight of the soil above that level, fluid pressures, and the stress introduced by the externally applied load. So the weight of the soil is neglected as soil is assumed to be wetless. So the external load applied, that external load, what much stress produced at specific cross sections, specific point below the ground surface become important. Over here, the load is applied at a point on the surface, and the stress developed due to application of that load at any point below the ground surface is calculated, right? So over here you see, as what I have made in the first slide only, over here you can see that let me take the ledger so that I can show you better. Okay, over here you see that this q is the applied load, and we want to calculate the stress developed at this point for the three-dimensional plane. In this plane only, the three-dimensional and two-dimensional both is mentioned. If you see the figure A and figure B, figure B is showing the polar coordinate. Over there you can see the theta, x and y, and sigma z, sigma x, sigma y, tau x, y, everything is mentioned in both things, but over there the theta is mentioned, that is the polar coordinate system, and this is the our xy coordinate system, Cartesian coordinate system, whatever we say, as I recall, right? So for the three-dimensional space, if load Q is applied over here and we want to calculate the stress at any cross section distance x, y, and z in the three plane, so we calculate the value of r as root under x square plus y square plus z square. Initially, during the discussion at the first slide only, I have mentioned that for the calculation of stress at any point below the ground surface, the R is calculated as root under x square plus z square. Over there I have mentioned because the z depth I have taken as I recall. So over here the y x square plus y square is the distance below the ground surface at which we want to calculate the stress. So for the two-dimensional, that is mentioned. For the three-dimensional, this thing is mentioned over here. In the figure B, the similar polar coordinate theta is presented, and when we see the equations which is mentioned in the next two to three slides, you come to know that in the polar coordinate system the equations get developed in term of r and theta only, while in the Cartesian coordinate system it is in the term of x, y and z. If it is a three-dimensional plane and if it is a two-dimensional plane, depending upon the downward direction is taken as z or y, it is kept in the term of x and y or x and z only. Now see that for the rectangular coordinate system, the sigma z is given as 3q by 2 pi into z cube upon r5. Well, these are the very equations over here mentioned. So that you just read and understood, but that need not to be remembered to solve the any field problem. Not only in the examinations, once you become the engineer at any company or maybe consultation firm, over there one also you have required to calculate the stress develop. So the equations which we normally used of the Bosniak equation is written as 3 by 2 pi. Okay, let me write over here first of all. After that, in some slide later you see that this equation is only, and the equation is like that 3q by 2 pi pq by 2 pi z square, where z is the depth, 1 by 1 plus 1 by 1 plus r square plus z square root. Okay, so I will dictate only because I could not able to write very clearly. This value is going to come to be 3q by 2 pi z square multiplied by 1 plus root under r square plus z square. Right. So, this value is only much important when we calculate the Bosniak equation. But some more point you need to understand that what is the r, what is the z, what is the q. So over here Q is the load which is applied. As you have seen from this slide, the Q is the load applied at the soil cross section. With respect to that, we are going to calculate it, the stress developed at various cross sections, right? So over here you see that the sigma z, sigma x, sigma y equations are mentioned. In addition to that, tau zx, tau xy, tau yz is mentioned. In the previous slide you can see over here that uh, all the things like the sigma x, the stress in the x direction, sigma y, stress in y direction, sigma z, stress in z direction, which is compressive over here. And in addition to that, the shear stress like the tau xz, tau yz and tau ix, everything is mentioned over here. Those equations is given for that. So now we have in the polar over here in the rectangular coordinate system or the Cartesian coordinate system, it is mentioned. In the polar coordinate system also we have mentioned the equations for the stresses in term of r and theta. The stress is mentioned over here. Okay, what equation I am discussing about, which I could not able to write over there, is this equation only. And these equations contain This is the basic equation, basic Bosniak equations which we use. And we calculate the sigma z as 3q by 2 pi into z square equal to multiplied by 1 by 1 plus r square by z square to power 5 by 2. Okay. Over there, I am writing something different, and maybe in a hurry, r square plus z square I am mentioning, that is not r square by z square by power 5 by 2, where z is the depth, right? So this equations is utilized in order to calculate the stress at any point below the ground surface. Okay, let me give me a minute. Okay, so this is the only equation which you need to remember and recall at any point of time. In addition to that, from the Bosniak equations and Westergaard equation, there is a equations for the line load is also there, like 2q by pi x into 1 by 1 plus r square plus z square whole square. Okay, so that thing if is not the point of discussion of this class, but as I have said in this class only, that when we going to solve the problems associated with these topics of the competitive exams, like engineering services or the GATE, over there you see some other equations, or I will also provide a formula sheet in the form of PPT only, that will be helpful for you to revise those concepts. Maybe at the end of the all classes, or maybe in the 8th or 10th lecture, whatever feasible for me and will be required for you. Okay, now we move to the problem associated with this. Okay, so the question what I have mentioned earlier, that it is a similar problem. Okay, so question asked, it is the application of Bosniak point load formula, that is nothing but 3q by 2 pi z square into 1 by 1 plus r square plus z square plus 5 by 2, and this is sigma z is also written as kb into q by z square, where kb is called to be Bosniak constant, which is 3 by 2 pi into 1 by 1 plus r square plus z square whole power 5 by 2. So you can see over here that the question asked that the for a square footing of size 3 meter by 3 meter subjected to a pressure of 100 kilopascal. For this load, find out the vertical stress at any depth at 2 meter, at any depth, but it is mentioned that at 2 meter depth below the center of the footing. So the solution is already mentioned, but I have discussed this in little bit elaborative form. But let me read over here. Then we move to, I have as I want to solve it with pen and paper only, but I could not able to write with the mouse in so much fluency, so I already kept the solution in the PPT, but I will elaborate over here, right? So over here you see that the total load is 9 into 100, that is the 900 kilonewton, because for a square footing of size 3 into 3 meters subjected to pressure of 100 kPa. So pressure of 100 kPa means 100 kilonewton per meter square. So then its load become 100 kilonewton per meter square multiplied by 3 meter into 3 meter means 900 kilonewton. So we consider a point load of 900 kilonewton at the center of the footing, substituting z equal to 2, because we want to calculate the vertical stress at depth of 2 meter below the ground surface, and there is r is doesn't mention, so it is just below the ground surface itself. So 1 by 1 plus r square by z square becomes 0, so it is 3q by 2 pi z square only we are having the calculations. So again, little bit elaborative form I have written this. So again, we have read the question and understood the question. Let's see the solution in the elaborative form. That doesn't require also, but if you are solving for the first time, you may get confused. So I kept this in the presentation, so that will be helpful in your better understanding of the topic. So see the square footing 3 into 3 meter carrying the pressure of 100 kPa, and we have to find the sigma z, the stress at depth z equal to 2 meter directly beneath the center only. So we have replaced the uniformly loaded 100 kPa with Q, which value comes to be Q multiplied by area, that is 100 multiplied by 3 into 3. As I already mentioned, 100 kPa means 100 kilonewton per meter square. 100 kilonewton per meter square multiplied by 9 meter square gets converted into 900 kilonewton. Now we use the Bosnian equation 3q by 2 pi z square into 1 by 1 plus r square by z square per power 5 by 2. Over here, it is already mentioned that we have to calculate the stress directly beneath the center. So value of r is going to be 0. Hence, 1 by 1 plus r square by z square, in which the 1 plus r square by z square become 1 because r is 0. So r square by z square becomes 0. So 1 to power minus 5 by 2 is 1 only. Hence, we need to calculate sigma z as 3q by 2 pi z square only. Q value is already calculated at 900 kilonewton. Z value, we know that we want to calculate the stress at the 2 meter below the ground surface. So hence we calculated the stress as 107.4 kilonewton per meter square. If we want to write in kPa, it becomes 107.4 kPa. Okay, I think so. Up to this, there will be no problem in these questions. Now we saw some more problem related to similar problems, so that it will give you the better insight of the Bosniak equation. So next question is based on the previous question itself. What it asks, let me read. So over here, this is not the question. In the next slide, question is there, but some points are mentioned over here about the previous slides one. Over here, it is said that the more accurate value can be obtained using the same Bosniak formula, but with the suitable modification. The entire foundation area can be divided into number of small units, and the Bosniak formula can be applied on the small units. And finally, cumulative effect of all parts at any desired location can be obtained by summing them. The smaller the unit size, better is the accuracy. The same problem can be solved by dividing the foundation area into 4 small parts and 9 small parts, and its effect on the final result can be seen. So what they are saying, that in this problem we have calculated by multiplying 100 kPa into 3 into 3, but we could divide into 4 equal area. We calculate the suppose this is 1.5 into 1.5, and this is also 1.5 into 1.5. We calculate the stress from this at this point, and then sum all of them. Then also we could able to calculate the stress. As the area get confined, as area get converted from 3 into 3 to 1.5 into 1.5, its accuracy get also increased. In addition to that, we can also cut out into the 9 section, in which 1 into 1 meter cross sections remain over there, and then also we could able to calculate the stress. So let's see. I have also calculated the same, because the next slide is related to that problem only. So I think so the thing will be clear. As you know, if you must have read survey, so over there is a concept whole to part, or like this. So if the big area is there, over there we have a very poor quality control in the um, building material. Also you have seen that the number of cubes required per 50 cubic meter, or maybe whatever, it gets added 4 per addition of 50. So over there also, once the size is very large, the quality control is the problem. But at this point of time, we are not concreting or doing anything like that. So quality control is not the concern, but the problem is that if we are not able to, we consider very large area, our stress value obtained at a specific point may be deviate from the actual value, but that not the case like that it will deviate too much. Just for the verification purpose we are going to solve this once more. It will be more or less similar value only. So you can see that it is divided into four, like q1, q2, q3, q4. So I already say 100 into 1.5 into 1.5, it get the value of 2.25 kilonewton. And okay, and let me read this thing, and then the elaborative solution we will see in the next slide. Okay, so it is seen over here that load in each unit like q1, q2, q3, q4, each 100 into 1.5 into 1.5. How? Let me use the pen and explain the things to you. You remember this is the 3 meter, and this is also 3 meter. If you recall the previous problem, it is 3 meter into 3 meter. We have divided into four cross sections, so it get converted into 1.5 into 1.5, 1.5 into 1.5, 1.5 into 1.5. Now 1.5 multiplied by 1.5 into 100 kPa is get converted into 100 into 100 into 100 into 1.5 into 1.5. So 100 to 2.25 kilo, 2.25 kilo Newton. So at the same depth of 2 meter below the center of the foundation, we have to calculate the value of stress. So now Q1 can be applied at any part, and stress can be calculated below the center of the footing. Distance from the center of the footing to that point, R is also need to be calculated. So R value is found as root under 2 square plus 1.5 by 2 square. Let me calculate this. Give me a minute. I'm calculating something. Okay, so basically what we are calculating over here are is like this. We want to calculate this distance, and this distance is 1.5 by 2, and this distance is 1.5 by 2. We are interested in calculating R. So the R value is found. R is big R or smaller R. I am writing big R only. so that not get to be confused. So it is 1.5 upon 2 square multiplied by 2. Why? Because this distance from this point to this is 1.5 by 2, and this distance from this point to this point is also 1.5 by 2. So 1.5 by 2 square plus 1.5 by 2 square root under is the r, and z is already known to us, that is 2. So let me 1.5 by 2 square multiplied by 2 root under is 1.06. So this value of R1, R2, R3, R4 all are going to be 1.06 meter. Hence, we could able to calculate the value of delta P1, which is going to be get to be 14.46. How we calculate delta Q1? We have calculated delta Q1 as the 3Q1. Q1 is nothing but 2.25. 3Q1 by 2 pi Z1 2 pi Z square, that is z is 2 only, and 1 by 1 plus r square by z square, that r value is 1.06. This r value is 1.06. Okay, so in this way we have calculated the value as delta P1 as 14.46. When we multiply 4 into delta P1, it comes to 57.85. Let me explain this with little elaborative form. So over here again you can see that Bosnic point load superpositions with the 4 equal load we are going to take. So footing is of the 3 meter into 3 meter. With uniform pressure of 100 kPa, divide the 4 square equal squares as you have, as I already mentioned over here, as 3 1.5 1.5, and so 1.5 into 1.5, this is like this. This is 1.5 and this is also 1.5. So 1.5 into 1.5 square, each is get converted. Now Q equal to Q into A1 equal to 100 into 1.5 into 1.5 equal to 225 kilonewton. Now R, as I have explained, that this is the load positions, and from here to this distance and here to this distance is 1.5 by 2, and it is also 1.5 by 2. When we calculate 0.75 square plus 0.75 square, we are able to calculate this distance R as 1.06. Now we use the Bosnian vertical stress from point load delta P equal to 3Q by 2 by Z square, that is 1 by 1 plus R square by Z square power 5 by 2. When once we use these equations, we are able to calculate delta P1 as 14.46. When we multiply 4 into delta P1, we get as 57.9. And if you remember, and that when we calculated from a 900 kilonewton load, we are getting the answer of 107, and over here when we convert it to the 4 equal cross sections, value comes out to be 57.9 kPa. So it is a huge difference between those two values. If you could not recall, I will show you in that slide. Over here you see that it is the 57.9 for the same problem, but when we have calculated the 900 3 into 900 by 2 pi into z square, this value comes to be 107. So this is the big difference between those two values. Now I will suggest you, now you take another cross sections in which you divide this load into 9 equal part like this of 1 into 1 meter each, and then calculate the stress at center and found that what value you are getting, and this will also give you the better understanding of the topic. So before moving to the next, okay, I think we can take a small 5-minute break and then we will start. So in the meanwhile, I will suggest you go through this problem, read this problem, understand this problem, and try to solve this problem. Not try to solve it, but just read this problem and get understanding that what this question is trying to ask. Uh, Once we start after our small 5 minute break, we will start from here only, and we will elaborate the things in more detail. Or maybe wait. Solve this problem only. Solve this problem only. Considering it is 1 into 1 meter. 1 into 1 meter. Basically, in the 9 equal cross section, we have used the 4 small at this point of time. You use 9 small parts and calculate the stress at the center. I think everyone could able to calculate. The Q value is nothing, but I will show this problem. This is the main problem now. Solve this problem considering the 9 equal sections of 1 into 1 meter, and what value you are getting. Try to solve in a small 5 minute break, and then we come back and start solving with that problem which I am showing over there. Okay, so over here the 5 minute break. Okay, welcome back everyone. I think so. If you have tried in this meanwhile to solve that problem, you could able to do so. Um, I feel that value, if you calculate it by assuming the 1 into 1 meter of cross sections, and that value might become less than the 57. Okay, let me move to the screen. Okay, my screen is visible to everyone now. Rayan, my screen is visible. Okay, okay, thank you, thank you. Okay, so what I have asked that solve this problem with the 9 small parts. So I feel that is the very easy thing. If you have calculated from for the 4 small part, you could able to calculate for the 9 small part. But let me draw once so that you could understand that what I want to say. Okay, so okay, this is not to scale, but what I want to mention that okay. So still it's not very to scale, but when you divide that thing into the small cross sections, so over here you could able to see that this is 3 meter, and this is also 3 meter. Now this is 1 meter and this is 1 meter, and so on and so on, and this is also one, this is also one. So now you have to calculate the value of stress at this point, and so for this cross section you need to calculate the value of r. So value of r is going to be 1.5 and 1.5 for this cross sections, for this cross section, for this cross section, for this cross section. But value of r from here is nothing but 0.5 plus 0.51111. So in that way you could able to calculate. So just for understanding, I have drawn this, so you could able to solve using the 9 small parts, and this will be very easy but quite interesting. If you are interested, please solve. Okay, now move to the next problem. The next question say that a system of isolated footing for a building block is shown in the figure. The size of each footing is 1.8 meter into 1.8 meter, and each footing exert a pressure of 287 kilopascal on the underlying soil layer. Determine the vertical pressure at depth 3 meter below the center of the footing 1, 2, and 5 as shown in the figure. Okay, I could not see that what is the 1, 2, 5, but let me see. And the pressure exerted by the each footing can be assumed to be single equivalent load acting through its center. Okay, so over here you can see that the 4 meter center to center spacing is there, and 3 into 3 cross section is there, but and 287 kPa pressure is applied. So over here you can see the grid of soil is 3 into 3, each footing, okay, each footing size, the footing size is 1.8 meter into 1.8 meter, with the uniform pressure of 287 kPa. So we could calculate the load coming out on the each of the footing, and center to center spacing in both direction is 4 as shown in the figure. In addition to that, the depth where the pressure is required is at the depth of 3 meter, sorry, depth of 3 meter below the center of the footing. Uh, means below the center of this, we need to calculate the sigma z value. Okay, so first of all, we have calculated load per footing, that is nothing but 287 into 1.8 multiplied by 1.8, that is 929.88 kilonewton. Now we know the Bosniak equation as sigma z at any depth or at any distance is 3q by 2 pi z square into 1 by 1 plus r square plus by z square whole power 5 by 2. Now at z equal to 3, uh, for the centermost part only, it comes to be 49.332 kPa. Now sigma z could be written as c by 1 plus r square. Z is only 9 only, but r get varied for different. For this, r value is going to be 4 root 2 for all the corner one, but for this r value is going to be 4. This for this also it is 4, for this also it is 4, for this also it is 4. So this could be generalized because 3q by 2 pi z square remain constant, so it could be written as c, and 1 by 1 plus r square by z square to power 5 by 2, so r square by 9, because z always remain 3 only, so this equation could be rewritten as in that format. Now for footing 5 meter center, the value get varied, the different r value is calculated, and the below the footing corner, the sigma z is calculated as 59. Below the footing 2, which is calculated as 63.7 and 69.1. Basically concept you understood. This slide you don't give too much importance, but if you calculate confinedly, you would get the value for the respective questions. Okay, I think so understanding will be clear for everyone, or I need to define, explain the r. I don't think so anything needed. The r value for this, let me take a laser. Question is like this only, and this center to center distance is 4, what I recall, and we need to calculate r value for this. So this is also 4, and this is the distance which is said to be r. Okay, so r value is going to be small r or capital R, that doesn't matter. R is root under 4 square plus 4 square. So it is going to be 4 root 2, right? Similarly, this value is also varied for this, and for this. Now we need to calculate r for that, for this, and this, and this. So this r value is nothing but 4 only. So R1, you can say R1 H. So I think so thing will be clear for that. So now there will be no confusion in this. I'm going to again to the PPT, and once I go to PPT, this screen will not be there. So I feel no more discussion is needed how to calculate the R value. So in order to calculate stress at the center. Okay. So the thing is clear in with everyone. Let me move to the next problem. Okay. So now you see the vertical stress distribution. The next question say that the calculation for below the footing number 5. Okay. So this is the continuation of the previous problem itself. Okay. This is the continuation of the previous problem itself. So the solution is mentioned over here that as I have mentioned, the R value is 4 root 2. R value is 4 root 2. That is nothing but 5.66. The another R value is 4 itself. That is shown in the delta P1. In delta P2, the R value is 5 root 2. That is mentioned as 5.66 square. And for the stress which is acting on the centermost cross section only, that is this is on this cross section, at that R value is coming out to be 0. So for that you have seen over here delta P naught equal to 49.338. So overall delta P value is coming to be 3.836 plus 1.111 plus 49.338 as 69.13. This is again discussed separately, and this 69.13 is written as 69.2 approximate value. So I think so the discussion related to same is clear with everyone. Yes. Now we are moving to the some other things related to vertical stress. As I have mentioned very early in this class that we can also calculate the vertical stress for the line load, circular cross sections. So over here, vertical stress under the center of the circular footing is mentioned. So it is worth mentioning that the unit vertical stress on any given depth could be determined with the acceptable accuracy by extending the Bosnick equations to the uniformly loaded circular area. So for the Bosnick equation, sigma z is written as 3q z cube by 2 pi from 0 to 2 pi and from 0 to r, like this equation is mentioned, but that not very important in order to derive, but integrating what result came is going to be important. So over here, the sigma z is mentioned as 1 q is nothing but capital Q by z square only, q multiplied by 1 minus 1 upon r square by z square plus 1 per whole power 3 by 2. So this equation is very much important when we are going to calculate the stress get developed below the circular footing. So this equation is also very much important. This you need to remember. So this is very, very important. Right. Now, you see The next question is rectangular area. The corner formula is there. So over here we integrate 3q z cube by 2 pi 0 to a 0 to b dy dx s square y square z square whole power 5 by 2. So derivation is again is not the part of the important, but what we come across is the sigma z equation like this, where m is a by z and n is b by z. Okay, m is a by z, z is the depth, and n is b by z, where b is the other depth, and from that we could able to calculate the sigma z value. This equation is not used very primarily, but okay, there is equation, but I don't see any problem associated with this question could be asked ever. But if it would be asked, the formula must be there, but you need to understand that what is the value of m and n. That might not be mentioned over there. Okay, so the vertical stress we could calculate at the corner, we could calculate at inside any portion. How we calculate the R we already understand, on the side and as well as outside. So numeric procedure is also explained in that directions. So the expression for the vertical stress under the center of the load of the circular given area is given as sigma z equal to q into 1 minus 1 by r square plus z square per whole power 3 by 2. Or when we rephrase it, we could write as sigma z upon q equal to 1 minus 1 by 1 plus r square by z square per whole power 3 by 2. So the sigma z by q versus r by z graph could be created, and for that when we do some calculation considering some value, this is a table is mentioned over here, and on that basis you can see that r by z value is mentioned as 1.39 1.91, and on the basis of that we could able to calculate by 1 by uh, um, 1 by r square by z square. So in this manner we could able to calculate the things. Now see the steps which we could follow in calculation of development of stress using the numeric chart method. So first thing come in the light is that this method in this method, first of all, draw a line for any length representing the depth. Find out the R for different sigma z upon q ratio, say R1, R2, R3, or R11, whatever we think. Okay, and delta sigma is going to be I into n into q. Now, draw a circle with the different radius. So, obtain and draw the radius lines dividing the whole circle into the 20 equal parts. So the whole area get divided into 10 into 20 equal to 200 division, and the influence value of each small block is 0.005. Now the length of the line so chosen for drawing the diagram taken as desired depth at which the stress to be calculated and drawn the whole area in that scale. Now cover the chart with the scaled drawn area, keeping the point of intersect on the center of the diagram, and then count the number of blocks covered by the diagram. Finally, the stress at that depth is given by delta sigma equal to I into n into q. So these steps are followed. Once the questions are associated with this will come, I will explain the thing, but these are the steps through which we solve the problem. So let's see, once the question get appear, I will explain it more detail. But in general, in day-to-day practice, also we use numeric charts, but not up to that extent. Now, what is this? I don't know. That repetition of that numeric chart is also there. You see that mn is equal to 200, 1 by 200 is equal to 0.005. Influence value is mentioned over here there, and r by z value for different things is mentioned, and how we draw the line and calculate the things each defined over here. So that's not the problem. Now we move to the next problem, and the problem associated with the vertical stress application only. Question asked that the base of the tower consists of the equilateral triangle frame of 6 meters each, on the each corner of which the column of the tower is supported. The total weight of the tower is 600 kilonewton, which is equally shared by all three columns. Compute the increase in the vertical stress in soil caused by the load of the tower at zero point 0.5 meter below the one of the columns. Okay, so let me read the question again, because it will give the clarity about the problem. So again, let me read this question. The question asks that the base of the tower consists of a equilateral triangle frame of 6 meter each, on the each corner of which the column of tower is supported. The total weight of tower is 600 kilonewton, right? The Q value, capital Q value, which is equally shared by the three columns. Okay, Q by 3, 200. Compute the increase in the vertical stress in soil caused by the load of tower at zero point 0.5 meter below any one of the column. Okay, so simple problem is there. What is given? Given is that the equilateral triangle of 6 meter. Basically, all the sides are 6 meter. The three column is there on each of the corner. The total weight of the tower is 600 kilonewton. The load per column is 200 kilonewton. The depth below the column z equal to 5 meter. We need to calculate the development of stress below any one of the column. Now, increasing the vertical stress at zero point 0.5 meter below any one of the column, we need to evaluate. In order, in that direction, we are going to apply the Bosnick equations to calculate the stress. So first of all, we calculate the stress on the column just below that, so that the value of R is going to be 0. So delta sigma z is, what is, we remember formula as 3 by 2 pi into q by z square multiplied by 1 by 1 plus r square by z square ka whole power 5 by 2. But as the value of r is 0, 1 by 1 plus r square by z square ka whole power 5 by 2 become 1. Hence delta sigma z for the stress below the point load of the column is mentioned as 3q upon 2 pi z square. Now the capital Q value is known to us as 200 kilonewton. The Z value is known as 5 meter. So we could able to calculate the delta sigma Z as 3 into 200 upon 2 pi into 5 square, which ultimately by after the calculations comes out to be 3.82 kilonewton per meter square. Now, the increase in the vertical stress in the soil at 0.5 meter directly below the one of the column is 3.82 kilonewton per meter square. But the question also asked the effect of other two also, no? I think so. Let me see. The question say compute the increase in the vertical stress in soil caused by the load of tower at 0.5 meter below one of the column. I feel that something missing in this problem. This is calculated below one of the column, but when we need to calculate the stress develops due to the influence of the 200 kilonewton load of two other cross sections. This is like this. This problem is like this. See like this, and the load is applied at all the three cross sections. Okay, so load is applied at all these three cross section, right? Uh, and we have first of all calculated its impact just below this only. Afterwards, we could interested in calculating the stress impact below this due to this load of 200 kilonewton and this load of 200 kilonewton. So in that directions, the value of R is also need to be calculated. So that value of R is going to be 6 meter only, and Z is already known as 5 meter. So we could able to calculate that value, and at the end we sum up all that, and we come to final solution. So this will be homework for you to solve the entire problem. Over here it is a partial solution. Okay, let me write also. Right. Okay, so this is the homework for you to solve it entirely and mention the answer what you are getting. Okay, let me move to the next problem. The next problem say that the 9 square footing of equal size 1 meter into 1 meter are arranged in the square pattern, three in each row, three in each column. Each footing carries 60 kilonewton load, and the center to center spacing of the footing is 1.8 meter. Determine the vertical stress at the depth of 5 meter below the center of center below the center of one of the corner footing. Okay, so let me again take a new slide and explain this. So he's saying that 9 square footings of equal size 1 into 1 meter are arranged in the square pattern, uh, 3 row, 3 column. Okay, so okay, so something like that. The question is asking that we have a 9 square footing are there, each of 1 meter into 1 meter, and each footing carry a 60 kilonewton load, and center to center spacing of footing is 1.8 meter. Okay, so this is 1.8 meter, right? So this is the thing already mentioned in the problem. Okay, so this much is mentioned in the problem. Now बोल रहा है determine the vertical stress at depth 5 meter below the center of one of the corner footing. So suppose this is our target footing below which we need to calculate the value of the stress due to the entire load acting on each of the column. So for this, the R value is going to be 3.6 square plus 3.6 square. for um, okay, let me explain the thing orally, then we move to the solution and you will get the better understanding of the things. So for the let our target footing of below which we are going to calculate the stress maybe 3. So the R value for that is going to be 3.6 square plus 3.6 square root under. You understood why? Because the distance from for the column 3 from column 7, if we are calculating from column 7, it is 1.8 plus 1.8, that is 3.6, and it is 1.8 plus 1.8, 3.6. So 3.6 square plus 3.6 square is going to be R value for 3. So R value for from 1 is going to be 3.6 itself. R value from 9 is also 3.6 itself. R value from 2 is going to be 1.8. From 5 it is 1.8 square plus 1.8 square root under. From 6 it is 1.8. From 4 it is going to be 3.6 square root under plus 1.8 square root 3.6 square plus 1.8 square root under. So in the tabular form we have I already mentioned in the solution, but for your understanding I have explained it orally. Now move to the solutions so that you will understood the things in a far better manner. So see, first of all, it is given that the number of footing 9 arranged into 3 into 3 squares as it is mentioned in this slide, and the size of each footing is 1 meter into 1 meter, and load per footing is 60 kilonewton. Center to center spacing between the footing is 1.8 meter. Depth below the footing where the stress is calculated as 5 meter, and calculate the vertical stress at the 5 meter depth below the center of the corner footing, and that corner footing is target footing we considered maybe as 3. Now let's see over here by XYZ direction, it is already mentioned the distance, so we could able to calculate the R. So first of all, see, set the contour, set the corner footing as center as 0 0, and the other 3 into 3 we put the X and Y value. So first 0 0, second is 0 1.8, third is 0 3.6, and in this manner we calculate the value of R. In this manner we could able to calculate the value of R. In this manner we could able to calculate the value of R for all the footing, and as I already mentioned, 1.8, 3.6, 1.8, 2.55, that is 1.8 square plus 1.8 square, 1.8 square plus 3.6 square, which is 4, for column 4 in our picture is mentioned over here. And subsequently, when the value of R is calculated, now we use our Bosnick equation to calculate the vertical stress as 3q by 2 pi z square equal to 1 by 1 plus R square by z square power 5 by 2, where q equal to 60 kilonewton as mentioned that for all the footing, and z equal to 5. So we could summarize it as 3q by 2 pi z square remain constant as 1.146, and now we are going to calculate D, which may be mentioned as 1 by 1 plus 1 by R square plus Z square per whole power 2.5. So the value of R square by Z square is for 0 0 is this, and hence the value of D is calculated. So the value of delta sigma Z is calculated. Once the delta sigma Z value is calculated for each of the cases, now we will sum that delta sigma Z value, and the final answer comes out to be 5.117 kilonewton per meter square, which is written as 5.12 kilonewton per meter square. The stress developed below the corner, stress developed due to all the footing below the corner, each comes out to be 5.12 kilonewton per meter square. Now, I think so the thing will be very much clear in each and everyone mind. So there will be no confusion regarding these things. Let me move to the next problem. We are moving toward the summing of the today's sessions for the problem which has been discussed in the class. Additionally, some other problems is also kept by my side in order to elaborate the things. So let's see in a meantime how much we could able to cover. So over here you see the question say that a annular footing with the inner and outer radius of 6 meter and 8 meter, 6 meter and 8 meter respectively is supporting a tank which extend a pressure intensity of 200 kPa. Determine the pressure increase at the depth of 5 meter below the center of the footing because of the foundation pressure. So, okay, no problem over here. Okay, let me read the solution. And the solution says, let's treat the annular footing as a difference between the two uniformly loaded circular area, outer disk radius b equal to 8 meter and the minus the inner disk radius a equal to 6 meter. Now we use the Bosnick result for the vertical stress under the center of the uniformly loaded circular area. So the for uniformly circular area, the radius r with the surface pressure Q, the vertical stress at depth Z under the center is given as Q into 1 by 1 plus R square by Z square per whole power minus 3 by 2. So for the annular footing contribution, delta sigma annulus become okay. So this thing we haven't discussed in the today class, so there might be some confusion. So the A by Z, M and N term we have discussed, but and the solution is made it in different terms. So let me see that how I will put it in the PPT so that you could get the better understanding of the thing, because I could not see that what we discussion we have made could make the solution very understandable. So let me see that how I will explain the things in the PDF which I shared with you. Okay. So with this, the this lecture is coming to the end. Now we will discuss some other questions related to the present topic which I have made. So first of all, in some problem the solution is not mentioned. You could answer those questions, but followed by the solution is already mentioned. So the first problem say that the Bosnick theory assumes soil mass to be homogeneous and isotropic, layered medium and isotropic medium rigid body. So the in the very first slide only the assumption, any very second or third slide only, the assumption of Bosnick equation is mentioned. Over here, there we say that it is elastic, homogeneous, isotropic, and semi-infinite media. So homogeneous and isotropic is the correct answer. So option A will be the answer for this problem. बिल्कुल सही, absolutely right. So now we move to the next problem. Next question asks, the Westergaard theory modify the Bosnick assumption by considering the layered elastic medium. Okay, we haven't this thing in the slides, but I feel that through problem also some understanding could be developed. So in order to do so, some problem which is not there in the slide is sorted, that the question through practice through questions is also very much important. So options are layered elastic medium. Okay, let me read the question again, followed by options. So the question asked that the Westergaard theory modify the Bosnick assumptions by considering the layer elastic medium, cross and isotropic soil reinforced layers, plastic medium or rigid soil. So the correct answer for this is option number B, that is the cross and isotropic soil, that is the reinforced layers. Now the next question say for the stress at depth Z directly below the load R equal to 0 and Z equal to 0, the Bosnick formula simplified as. So you have remembered 3 by 2 pi into q by z square into 1 by 1 plus r square by z square the whole power 5 by 2. As value of r is 0, that means the 1 by 1 plus r square by z square for whole power 5 by 2 becomes 1. Hence the option number B, that is 3q by 2 pi into z square, will going to be correct answer for this problem. So option B is the correct answer. Next question is again repeated. So let me move to the next slide to solve some more problems. So next slide asks that the vertical stresses decreases with depth in both theories, as both theory means Bosnick theory as well as Westcott theory. I have mentioned over here. Maybe so it vary inversely to z square. So because 3q by 2 pi z square, so it is inversely vary to z square. So option B is the correct answer. Next, at large depth, that z is very greater than r, both the theory, that is the Bosnick theory as well as Westgard theory. When it is written both theory, Bosnick as well as Westgard theory, predict the stress approaching zero in finite applied load intensity Q random value. So the option A, the stress approaching zero at the infinite depth. Okay. For the next question, the solution is also mentioned over here. So the question asks a point load Q of 100 kilonewton acts at a ground surface. Find the vertical stress at depth Z equal to 2 meter directly below the load using Bosnick. Okay, so you have remember the Bosnick equation as 3 by 2 pi into q by z square into 1 by 1 plus r square by z square per whole power 5 by 2. As the value of r is 0, that term become 1, is 3q by 2 by z square comes out to 11.94. So the closest option is option number C. Answer number C, option number C is the correct answer. Okay, then again this question is repeated, so that's not the problem. Let me move to the next question. Okay, from here onwards the question and solution all are mentioned along with, so that's not the problem. Let's go one by one. Yeah, over here the question related to Westgard theory for the same load and depth at shown in the question number 6, that at depth Z2 using the Bosnick Westgard equations, the solution comes out to be 7.96. So I don't think this could be explained at this point of time because we haven't discussed the Westgard equation, but let's leave it over there. The next part of the problem say that a point load of 200 kilonewton act at a surface at depth z equal to 5 meter and the radial distance of r equal to 5 meter. Find delta q as a Bosnick equation. Again, Bosnick equation say pq by 2 pi z square into 1 by 1 plus r square by z square to whole power 5 by 2. So we know the value of q as 200 kilonewton as mentioned in the problem, and the z is 5 meters, so the z square is going to be 25. The value of r is already mentioned as 5 meters. We need not to calculate. We have solved the more difficult problem than this in this class only. So the after calculation, the stress value comes out to be 0.38 kilopascal. So option number A is the correct answer. Next question say that for the same question using the Westgard equation. So leave it. We are not interested in this, but for the Westgard equation, the formula is like that: q by pi z square to 1 by 1 plus 2r square by z square to whole power 3 by 2. But leave it at this point of time. But I will kept it in the PDF so that you could able to understand the things. Again, the next problem is find the vertical stress using the Bosniak only. Over there, many things mentioned, so I don't think so. I will discuss this because I have already solved the many problems associated with the same. So you could able to solve this by yourself. This question will be there once I share the PDF. Okay. The next two problems is like if the ratio of R by Z increases the stress distribution according to Bosniak increases, decreases, constant, first increases, then decreases. So as the R by Z value increases, you understood the R by Z is in the second term, kV to Q by Z square. So if R by Z value increases, that term value, the ultimate value of 3 by 2 pi into 1 by 1 plus R square by Z square ka whole power 5 by 2. So R square by Z square is at the bottom section. If that value increases, overall value decreases. Hence, the stress distribution in the Bosniak theory also get decreased. Now, the next part of the problem say for the same load, Westergaard stress are generally higher than the Bosniak, lower than the Bosniak, equal or infinite. So it is lower than the Bosniak equation. Next question say a 200 kilonewton point load act at the depth 4 meter, stress R equal to 0, Bosniak equation. So that is nothing but 3 by 2 pi into Q by Z square. That comes out to be 5.96 kilonewton per meter square. So option number A is the correct answer. For the same question, it is asked using the Westergaard theory. So leave it at a required at this point of time for our reference. But in the 2q by z square and z is 0, so over there you could also solve, but that's not the things at this point of time. Now stress isobar. Okay, stress isobar represent the lines of equal vertical stress. Whenever term isobars comes, this means it connecting the equal point things. So it is also, you see, isoplate, isoplues, many more terms are there in the civil engineering. Some are isoheights in the hydrology, in irrigation, evapotranspiration. So over there, the many terms like that. If you come across the subject of chemistry during your 12th, isotopes, isobars, some other terms are also there. Now, the next question say at depth Z, the directly below the point load, the ratio of Bosniak stress to the Westergaard stress is 3 by 2. Okay, that's not the problem. When you write the Bosniak equation divided by Westergaard equations, this value comes out to be 3 by 2 for R equal to 0. And the next question say that the stress at depth under the center of uniformly loaded infinite area is 0 equal to q by 2 into infinite. So it is equal to q. Option number B is the correct answer. Next question say for the circular footing the radius r stress distribution depend upon the z by r value, while subsequently at the shallow depth z is very less than r, the stress below the center approaches 0, q by 2 or infinite. So option B is the correct answer for this. Next question say for the stress due to multiple loads, principle of calculation is superposition. Yeah, right. Because we have solved today many problems in which we have divided into 4 by 4 cross sections, 3 by 3 cross sections, 2 by 2 cross sections, and we calculated the stress. In additionally, we have also calculated the stress at the corner in which the 9 footing is there, the last most problem only. So over there we calculated the stress for each of the points, and then sum of that we have superimposed that the stress due to load applied at point 1, point 2, point 3 on the point 5 is evaluated, calculated, and stated. Now the next question is related to Westergaard, so leave it. Finally, in the last slide, in which we are asking for the rectangular loaded area, the stress can be computed using the influence chart cosmic superpositions, approximate formula, or all of above. So the all of above is the correct answer. Next is the depth of the significant stress influence below the footing is about 0.5 b 2b or 4b. So 2b is the radius of influence, basically stress influence zone is 2b. And the last problem of the day asks the settlement of the soil is mainly governed by the vertical stress increment, shear stress, core pressure, or the neutral stress. So in the very first slide only, we talk about the vertical stress increment is very much important when we talk about the stress distribution in soil. In addition to that, over there we also mentioned the impact of total stress, effective stress, and the core water pressure, which is widely discussed in the previous class. So up to that, I think so there will be no confusion. So with this, I am summing up the today class. So one important thing I want to mention over here, that please try to solve some problem associated with this topic. Additionally, some other questions which could be there in the textbooks, try to solve it with this topic and the other topic as well. That will be many more helpful. And from the next class onward, I try to solve some problem like some problem maybe that some problem like the question which will help you in the your competitive exams. So I try to uh, take those questions, and that will be very much helpful in your study journey in the academic field as well, like get or engineering service exam, because I feel the many of you may be preparing for those exams at this point of time. So thank you everyone for joining. Wish you a very happy weekend and see you in the next class. Thank you for joining. I am ending the today class.